So this is going to be more, not a continuation of Yashar's talk so much as an elaboration, so some of the points he made. I want to go into some qualitative detail about. For the few of you who don't know me, my name's Adam. I'm just finishing up my PhD in DAMT. Collaborators relevant to what I'm going to talk about are listed here. A lot of them are in this room, and they all deserve a huge amount of credit. Before I start going into the details, I just want to run through my motivations for working on bigravity. I think I'm probably the youngest and least experienced person in talking about bigravity this week, so of course you're all going to want to hear what I have to say. So the zeroth order problem, we have dark energy, we have a couple of cosmological constant problems, maybe modifying GR will help, and since GR is a theory, the theory of a massless spin zero field, a very straightforward approach to modifying GR would be to give the graviton a mass. So if we have a theory of mass and gravity, thanks to Claudia and Andrew and a lot of Fawa and other people in this room. How are the cosmological solutions? What's the state? The answer is not so hot. Remember from Claudia's talk that you really can't get stable FRW solutions in the pure sort of DRGT mass of gravity. So there are a few ways out. One, as Claudia mentioned, so let's look at inhomogeneities at large scales. Another would be to generalize mass of gravity, generalize DRGT. So there's this version where you break translation invariance by promoting the mass terms parameters of the Struckleberg fields, or generalizing the matter coupling, again, due to Claudia, Raquel, and Lavinia. And then the third way out would be to add new degrees of freedom. You want to be careful with this. So for example, if you're adding a scalar field, you can modify gravity with just a scalar and not bother giving the graviton a mass. So at a certain point, you want to make sure you're not just adding hats on top of hats. But in terms of adding the tensor degrees of freedom, so going to bigravity, it's sort of a natural thing to do because you already have a tensor appearing, and not an integral second tensor, appearing in the theory. Giving it a nice Hilbert term isn't the craziest thing in the world. So sort of by just explaining why you get self-accelerating solutions fairly generically in this theory. So we're going to couple G to matter. So G is the physical metric, and F is this kind of field which couples a G to give the graviton a mass. So the physical metric, we can give the usual conformal time form, so we'll have the usual scale factor A, same notation as we're used to from middle school. And then you will have F metric level lapse X and a scale factor Y. The dynamics are fairly nice. There's the Bianchi identity imposes a constraint which fixes X on a certain branch in terms of the Hubble rates of the two metrics. And then the diameter are entirely controlled, as Yashar mentioned, by this ratio Y, which is the ratio of the two scale factors. So once you know that, everything else follows. So you have a Friedmann equation for G, which is just the usual matter coupling plus a mass term, which is a polynomial in this ratio Y. And then because of this Bianchi constraint that fixes the lapse of the F metric, you have this really nice property that the Friedmann equation for F becomes algebraic. It just becomes this quadratic equation that's termed the evolution of Y. So one really simple example of how to look at these, just take the late time limit, right? So rho, say dust, goes to a to the minus 3. As that goes to 0, all the other coefficients in this equation for Y are going to become constant, because this is the only time-dependent coefficient. So Y is going to approach some constant, generically non-zero, and you'll see that the mass term also approaches a cosmological constant-like term. So just really straightforwardly, you can see you sort of expect to get late time acceleration, dynamical dark energy that's asymptotic toward the descent or light phase. So Yashar, Marek, and Tommy did a really nice statistical comparison of these backgrounds to CMB, supernovae, BAO. So he lists all the models here. So here's the model with only the beta 1 interaction turned on, beta 2, etc. We're using the capital B's, where you use to scale the betas by the graviton mass over h dot squared, so these should all be order 1 to get acceleration. Right away, you can see a lot of them are just disfavored massively by low p-values, so you can get rid of all those. Thanks to this paper here by Frank, I think it was his master's paper, because Frank's very good at bigravity, we have theoretical viability conditions, which can rule a few more out. And the nice thing is every model you're left with, which has a sensible background that agrees with observations, includes this beta 1 parameter, which is proportional to the trace of this here square root matrix. So right away that sort of picks out this, again, as I mentioned, this beta 1 only model as sort of the simplest minimal by gravity model. As we've seen, it has an instability, so we'll go into that. Going beyond the background, right, we want to study perturbation theory. There's a lot you can do in cosmological perturbation theory. There's a lot of papers about this, and this is just a singly coupled case. There's even more if you consider crazier matter couplings. So all these papers here looking at the perturbations. I'm going to focus on the approach that we've developed, me, Yashar, Frank, etc. Frank especially deserves a lot of credit for this. So we perturb the metrics, the perturbations look like such. You can find the full linearized equations in one of my papers with Yashar and Tommy. The Einstein equations you get are really complicated, right? But the usual thing you do when you have a modified gravity theory, one of the first things you want to do is take the sub-horizon limit and also sort of implicitly a quasi-static limit. So you want to focus on sub-horizon modes, which is where most of your observations live anyway, in galaxies and such. You take the wave number to be much bigger than Hubble. That's fine to say you're looking at modes that are deeper than the horizon. But you also assume that time derivatives of phi is a general perturbation here. You assume the time derivatives scale as h. And so that quasi-static approximation is only valid if your modes are stable. This is, I think, often taken for granted. It's only sort of experience in bi-gravity that's really been showing us that we need to actually solve the full system first to really check this assumption in detail.
Actually, on sub-Hubble scales, you usually get oscillations. So why do you say phi double dot proportional to h phi dot?
The amplitude of phi. So ignore the oscillations, the overall amplitude. Yeah. Right. So we want to actually go ahead and do this because, as it's been alluded to about 1,000 times in the last 2 days, this is going to fail for most biometric models. So we'll run through how we actually go ahead and do this analysis. There's a really nice story about the degrees of freedom counts in this, mostly due to Macarena Lagos and Pedro Pereira. So we'll deeply into them for that. So we have 4 metric perturbations for each metric, and then one meta perturbation that's in a kind of funny formalism due to Robert and others from back in the 90s. So you have these 10, sorry, that's a typo, should be 9 perturbations. And again, this should say 7 here, sorry. So 4 of these are non-dynamical. So in particular, the E and F, so these are the time-time and the time-space perturbations. They don't have derivatives, time derivatives, when you look at the second order action. So they're auxiliary variables, you can integrate them out and just get algebraic constraints. So you can write all 4 of these in terms of A, G, B, G, A, F, B, F, chi, and their derivatives. Furthermore, 2 of those dynamical variables can be gauged away, which would leave you with 3, right? But the really nice thing that happens, and this is very closely tied to the constraint that removes the polar Demeter ghost, so this very nice structure of these DRG potentials, is that, so let's say we gauged away, say, chi and, Okay, so we get rid of these two, we gauge away 2 of these, we have 3 variables left. One of them becomes auxiliary after we integrate out the auxiliary variables and gauge away 2 more. So the time derivatives of one of these 3 dynamical variables all just go away, which again is sort of the same as the absence of the ghost. And so you're left with only 2 independent degrees of freedom, which correspond to, say, the matter perturbations and then, say, the scalar mode of the massive graviton. So in our paper with Frank, Luca, Yashar, and Marielamoto, we chose our 2 independent dynamical degrees of freedom to be the Bardeen variables for the G metric, and then you can very straightforwardly reduce this whole complicated system of Einstein equations and fluid conservation equations to a 2D second order coupled system. So it's actually very straightforward. These F and S are just matrices that only depend on background variables. If you assume that these background terms, F and S, vary fairly slowly, so it's a WKB approximation, then the solution to this is very straightforward. It's just exponential. with some eigenfrequencies omega. And we prioritize things in terms of the number of e-folders. This assumption, Stolpe-KB assumption, is going to hold in the large k limit. So taking k over h to be very, very large, we can calculate these quite easily. So here's for the beta 1 model, which is the one that sort of was the simplest model that brings all the background data. What you find is, so bear in mind, so if omega is real, we have oscillating perturbations, everything's nice. If omega is imaginary, then we have exponentially growing modes, and that can be very bad. And especially since they are proportional to k, if they're growing, then you have a great instability, which, as I was saying before, is kind of disastrous. And sure enough, when this y is small, you're going to have a negative number inside the square root. You're going to have an imaginary eigenfrequency growing modes. So small y in this model corresponds to early times. So you get generically great instabilities at early times in this model up to redshift is about 0.5. So I've plotted here y, the ratio of the scale factors for this model as a function of redshift. So this is a finite branch model. So at early times, y goes to 0, and then at late times, it eventually asymptotes some constant. What you see is that for sort of all these redshifts below, it turns out to be about 0.5. Y is small enough that the thing inside the square root is negative, and you get this great instability happening. So this model is very nice in the background, but you can't use perturbation theory pretty much at all until extremely recent times, which is a bit of a problem. Because small y is the issue, you might very well think, and you'd be right, that these infinite branch models where y starts off at infinity and then goes to a finite value would be a lot better. So these infinite branch solutions are in fact stable. We found that. There's only one very specific set of parameters which will give you an infinite branch solution. That's if you turn on beta 1 greater than 0 for background viability, and turn on the F-metric cosmological constant. It's a funny combination of parameters, and it's got to be between 0 and 2 beta 1. And as long as you're on the infinite branch, then you can have stable perturbations at all times. So there's a really simple way to see this graphically. So I've plotted for this beta 1, beta 4 model how y prime, so dy d at number of e-folds, evolves compared to y. And this is useful because in this particular model, there's a very simple expression for these eigenfrequencies, which is just I times square root of dy prime dy. So if the thing inside the square root is negative, and the slope of this line is negative, then it cancels out the I, and you get real eigenfrequencies, you get stable perturbations. So the finite branch, when y starts at 0 and evolves to this center point. The infinite branch, y starts off infinity and evolves actually to the same point. And so you can see very clearly on the finite branch, at early times, dy prime dy is positive, so you get imaginary eigenfrequencies. And then you see this, how it stabilizes at late times, and the slope is negative. But on the infinite branch, the slope is always negative. And so at all times, you can see graphically from this that you'll have stable perturbations in this model. So at first, this seems like a really nice model. This essential background, there's stable perturbations. And there's a really cool thing, which is that because the parameter range for this model is so tiny, there's no lambda CGM limit. There's no choice of parameters, which brings the perturbations even near the lambda CGM predictions. So is this a good modified gravity model? See, yeah, so we call this infinite branch bigravity, IBB. One of my collaborators, who I won't name, proposed the infinite branch solution at first, but the acronym didn't catch on. And it's probably best that didn't. Back to this question of whether it's a good modified gravity model. Again, as Ishar alluded, the answer unfortunately is no. There's been a few papers recently, and you can see Frank's talk next week, showing this model has a huge ghost. And that's even worse than a great instability, because that makes the theory completely poorly ill-defined. So, very sad.
But there's also singularity, right? It's not only the ghost. Even without the ghost, this theory, I mean, in order to get to the late time, you need that. So, I mean...
it was never quite obvious whether passing to the singularity was a problem in the F sector. But I think at this point it's an academic question
Amazing.
because there's a ghost.
Otherwise, I mean, all the high gravity term in the gravity sector will be important and near to the singularity. So you can really trust your theory when you are very close to the singularity. Unfortunately, the singularity is basically now. So
Yeah,
we'll see.
fairly recently. Yeah, that might well be a problem. In the end, I think all these issues, tensor instabilities, bounds, the ghost overrides them. The ghost just kills the model, makes all these other questions academic, really. So in the end, this is actually extra motivation to see if the gradient stability disappears due to some sort of Einstein mechanism in time beyond the linear level. Because at least the simplest model would be the one model Matteo and Andrew have shown that the Gucci ghost is absent at all times. So as long as we can deal with the gradient stability, then there wouldn't necessarily be an issue. Right, that gradient stability, it's important to emphasize, it doesn't rule models out. It only tells you that you can't use linear perturbation theory at these early times. Nothing more and nothing less. So this is a problem calculationally. It means you can't use linear theory, and it means you can never take the quasi-static limit, which is a really nice calculational tool for understanding how structure forms. But in principle, the model could still be physically viable. We just need nonlinear techniques to understand how the perturbations evolve in this theory. Unfortunately, these have yet to exist. So this is a very much an open problem, which needs to be looked into. But again, because at least the simplest of these finite branch models is Higuchi-free, this is probably the main direction to go to state this theory with this matter coupling. Okay, so on the topic of the matter coupling, there's another way out we've been discussing, which is to consider more general matter couplings. My motivation that first got me interested in this question way back when I was a bi-gravity baby looks like this. The bi-gravity action in vacuum, so just the kinetic and the mass terms, it looks like you're treating G and F on different footing. You have G here, F here, so the mass term looks like it's treating these two metrics unequally. But because of the very symmetric nature of these polynomials, these EN polynomials, it turns out that if you flip the two metrics around, so interchange the two metrics, interchange the Planck masses, and interchange the beta parameters, so you interchange the cosmological constants, and then interchange beta 1 and beta 3 with each other, you end up getting the same thing back. I think symmetric is probably more of a duality, I guess. There's a metric interchange duality in this theory, which has been broken by the assumption we made that matter only couples to one metric. And so you might very well ask, is there a way to generalize the matter coupling so that the entire theory has this very nice property that both metrics are treated equally? It's almost like a culmination, right, of the philosophy led to bi-gravity. So you have DRGT, and there's a metric and a non-dynamical reference metric. And so you say, okay, why don't I give dynamics so that they're two dynamical metrics, and then you're constantly trying to find a way of making the footing entirely equal. This turned out to be really hard. So as Claudia, Levin, and Raquel showed, as well as this Yamashita et al. Group, generically, you'll reintroduce the ghost as soon as you do anything other than couple one matter sector to G and maybe one other matter sector to F. As far as we know, there's only one near way out, which Claudia mentioned yesterday, or did she not get around to it? I forget. I might have run out of time. The idea would be to couple matter minimally to an effective metric, which has this kind of interesting form. So this makes more sense in Vielbein language. It's the Vielbein of this guy is this linear combination of the G and F metric Vielbeins. There's a nice rationale for this, which is that matter loops would generate a term that looks like square root of the determinant of this metric. And that square root of that determinant is exactly of the form of a DRGT potential. So the metric interactions that matter loops will generate between D and F is ghost-free, which is sort of a necessary but not sufficient condition to have a ghost-free matter coupling. As a result, though, there's one of the nicest features of the theory is lost, which is the fact that in the singly coupled theory, the graviton mass and the structure of the potential are not, are sort of not destabilized by quantum corrections. And here they are because this overall scale will receive matter loops.
But not necessarily. Technical nothingness may not necessarily last if the scalar field couples to its massless.
Sure, if you have a massless or some sort of a symmetry. I think if you have, but if you generate a term which is like rho lambda times the square root, you should lose, right?
Because the scale.
Sorry, yeah. If you couple, say, the standard model to that, and if you couple the standard model minimally to G, then you can evade this. I agree. Yeah. So if you only couple G effective something like a massless field, yeah, then you don't necessarily have that issue. That is true. Okay, so we've done the cosmology, and I'll have to fast forward through this because I'm out of time, apparently. But the nice thing is, so for example, beta 2 only doesn't work in this theory, so that would be, you can see that the data don't agree with the beta 2 model in the singly coupled theory, which is down here. But when you turn on this coupling, you get more theories that we can work with. There are problems, so you maybe lose technical naturalness. There are instabilities. This has been shown. Unless you couple some matter minimally to the geometric, for example. And also you have the reappearance of the Bullman as it goes to very high energies. This might be okay from an EFT perspective. It might not. I think this still needs to be investigated. Good. Summary of points. Some bimetric models don't give good background. Some are unstable. Finding something which works is quite tricky. Your best bet is probably to look for something which has a great instability, but loses that nonlinearly, which may or may not exist. And there's also problems in direction. We have to be very careful if you want to consider more general matter couplings. So that's probably all.